know what this is a slide of, and we often ask you, or we can ask you, well, where would you find this? Okay, so we've gone through this. Whoops, sorry. Leave it right there. We've gone through this and kind of finished up rushedly, but we'll get through our last parts of chapter 4 here. All right, so also it's supportive because cartilage and bone are your supportives, right? Your propers are the dense, regular, dense, irregular, the loose areolar, right? So supportive, the bone is a really unique in its appearance. First of all, the slides generally aren't stained, right? Like the pinks and purples and so forth. They're usually to represent it because, again, the rock wouldn't pick up coloration so well. And the rock is all this stuff in between, right? These are layers of rock with the cells embedded in the matrix. Now, at one point, and here's a high magnification of a cell surrounded by its lacunae and its matrix, right? And so what you've got here is you've got 3 really important cells, and like the cartilage, we've got a special name, right? We added this word root chondro for cartilage. Well, I say, for bone, we're going to add the ost for os or ost, right? And these suffixes are what are going to be important. So a blast, anytime you see a blast, like fibroblast, well, it's a builder. Always think B for builder. They're the cells making the matrix, making the proteins. The sites are the mature, right? So these are usually immature, younger cells building up matrix. And then a site as a suffix, well, that means cell, and this is usually a mature one, that is, we often say, maintaining. They're keeping the matrix thickness, width, amount, right? So they're not as active as the blasts are, but they are very necessary. So then an osteoclast, in this case, that word root means it's a destroyer, right? So the clasts actually break down the matrix. And again, the matrix is rock. Your bone is rock. It's a mineral, calcium phosphate, inorganic salt, big one, big chain of these, right? But it's rock. And so often what throws students when you first talk about this, and we'll talk more about it in the chapters on skeleton, is, well, why would I want to destroy bone? What is the advantage of destroying my bones? They're my support. They give me shape, right? They are protective, like in my skull and my ribcage, so why would I want to destroy them? You're going to have to destroy them because of what is in this rock. I said it's calcium phosphate. So if your calcium levels in your blood are not high enough, right? Homeostasis, homeostatic constant. If they are not high enough, your body will direct the effort of restoring the calcium at the bone. It's going to start dissolving the bone. And in that circumstance, you're going to tell these cells to become very active. And they're going to really, literally start to release acids, and they're going to start dissolving your bone, releasing the calcium back into your blood. Because your calcium has to be available. Free calcium, ionized calcium must be available at all times. So if you are not consuming enough calcium, or for some reason you are getting rid of more calcium than you should, you're going to go to your bones. And that's why over a lifetime, this can lead to something like osteoporosis, right? Is if you've got people that have just not been paying attention to the calcium intake, and they are repeatedly going too low in their blood calcium levels, well, you're just going to keep borrowing from the bones. And I say borrowing because it can go back. It can go back if you get these guys activated, but they're only going to be activated if there's enough calcium, right? So in the converse, if you consume a lot of calcium products and they get into your body, well, then the osteoblast can simply take that calcium and stick it in the bones. Because again, we said homeostasis is about just right. Just right. So calcium can go too high and it can go too low. And the key to controlling it is going to be these cells. Right? So in the beginning, when you built your bone, because it didn't start off as bone, you know, as you go back to being an embryo, right? You formed all the structures of your skeleton, right? This thing right here. But it was all cartilage. So when we look at pictures of an embryo, we can see that they're a little human, tiny human, with fingers and toes and arms and legs and skull. It's all there, but it's cartilage. And so we're going to talk about this process of making bone, converting cartilage to rock. Because I need rock when I come out in the world. Inside a fluid-filled chamber, right, mom's uterus, I don't need that yet, but I'm going to. So in that process, your osteoblasts became active, and they just started making all of this. So again, we're going to go back, we're going to talk about that in future chapters, but and so what happens is, again, is they just lay down, they all line up on a regular area, and they just start producing and producing. So always in compact bone, right, and there's going to be a difference between, we're going to talk about compact, and we're going to talk about spongy bone later on, but in compact bone, and this is, there'll always be a hole right in the middle, and it'll look like just a dark spot for you guys. This hole lets a blood vessel through. Because if you're going to be an active cell, you're going to need oxygen and nutrients, right? I'm going to need all the stuff that cells need to carry on their own metabolism and do their jobs. And of course, you're going to need the calcium to do this and the phosphate. So you got to have a blood vessel coming in irregular intervals too. And so on your slides, no coloration like this shows you in this picture, and then there'll be this central dark area, fairly big. And so that would be where a blood vessel would come. And it would be feeding all these cells. So the dark areas are the cells themselves, the osteocytes. Because the osteoblasts, once bone is formed, and as you're looking at formed bone, are really on the outside of the bone. They really would be in an area like this, not throughout the whole bone. Okay? And so these are osteocytes, right? These little dark areas. And this is all, right, they have created just patterns of rock around them, right? So again, in the middle, right, is that central canal. So I said in the middle of an osteon. So the whole thing is called an osteon right here. And so your compact bone is a whole bunch of these concentric circles, right? Just a whole bunch of concentric circles. Now, if you understand what this means, these would be coming out like this, wouldn't they? In a three-dimensional object, these would be coming out. So your long bones, like your femur, are just pillars of concentric rings of rock. That is, geometrically, that's the best support you can get. I mean, that's why trees do it that way too, right? These are highly supportive patterns. That shows you what this tissue does really well. But never take the patterns for granted. They mean something. Just like I said, when you look at those, you know, cuboidal cells all squared next to each other. There's got to be a reason. And why connective tissue, it's more abstract and it's more spread out. There's a reason, all right? So that quite literally is extremely, extremely strong. So the whole thing here is called an osteon. So the bone itself, because this is microscopic, would be a bunch of these osteons. And I know we have some bone stuff in here. So, oh, here we go. So here's right a piece of like what you'd see. So this is just a little piece we've cut out of a slice of your bone. And we would just see, again, this is compact because it's all tightly packed. These would all be osteons, just all these osteons. And then they pulled some of them out to show you some of the other features of it. Okay, but that's what bone looks like. So we introduce these vocabulary terms and we say, okay, so the whole thing's an osteon. We've got the lacunae, like we talked about in the chondrocytes, which are the little spaces. But again, they're so tightly packed you can't see the space. We've got a central canal. Lamellae, well, lamellated means it's a layering. Lamellar, it's layers, all right? So lamellae are just each of these layers. So lamellae, right, layers, okay? Canaliculi, little canals. So here, you can't see it because we're so magnified here. There are little tiny tunnels, canals, that are running in the rock. And those little canals, which you kind of see how it looks kind of fractured here? See the black lines that are kind of radiating out like sun rays? Those are canaliculi. And so what it means is, it means that these cells, right, and you see it here, their processes, part of them is moving through the rock. But we have to have the little canals so they can reach out, right? Because otherwise I can't get through this rock. So there's little tiny holes in the bone, little tiny, that we call canaliculi, and these cells are really crazy in their shapes, like it kind of shows you here, right? And they're reaching out and contacting each other through the bone. So this cell is in communication with that cell and that cell. So, because remember, to function as a tissue, you got to be talking to each other, right? You got to know what's going on. And so this gives them the ability to do that, all right? So again, our bone gives us obviously strength and support. It gives us shape. It allows muscles, that's why they're called skeletal muscle, to attach. And this is where you're going to make blood cells, which we'll talk about some more. Right? This stuff is not making blood cells, by the way. These are clearly blood vessels, but we're talking about your red cells, right? All your red cells. So there are blood cells over here, right? All these cells here on this poster, all made within your skeletal system for the body. After you're born, all of them made. And they're made by this stuff we call red bone marrow. And red is acknowledging, right, the red of blood cells. Red bone marrow, okay? All right, which brings us to blood. Right, so here's another connective tissue, unique, specialized for transport. Right, so it's transport because it's in fluid. And fluid moves a whole lot better than solids, in case you didn't realize that, right? They're just easier. Fluid flows. All right? So most of your blood, you have several different types of cells in there for our intents and purposes. And like I said, if you want to see all of them, they're nicely shown on this poster here. But for our intents and purposes, we say we've got a lot of these red cells, or you use the term erythro because that word root means red. We have white, leuco means white cells. They look purple because it's been stained, right, with their white cells. And then we have thrombocytes because those are platelets. So all three of these groups of cells, because they all end in cyte, are made in your red bone marrow, okay? But then the red bone marrow releases them into these tubes, right, that you call vessels. And you specify by calling them blood vessels. And the tissue these blood vessels carry is called collectively blood, but it is made of the matrix plasma and then these cells suspended in this fluid. Okay, they're not dissolved, clearly suspended. Right? So a specialized connective tissue, anytime I see the word roots hemo or hemato, it's blood. Lymph is an entirely different fluid, but it's good to consider lymph here because a lymph fluid comes from the blood. In fact, every fluid in your body is going to come from blood. When we get to the brain and the spinal cord and we say it's bathed in cerebral spinal fluid, right, because it means brain and spine, that's going to come from your blood. When I look at your serous fluids, that came from the blood, okay? When I look at synovial fluids, to some extent that comes from the blood. Aqueous fluids, that comes from the blood. So the blood gives rise to all of these other fluids in the body. So we say that this connective tissue transports, does that really well. It distributes, so it gets things to a place, right? It defends, and that's really what these white cells do, and it helps regulate. That's its job. also regulate things like temperature. So when we get to skin and I say, look, it's getting colder out. I know you can't believe it right now, but it's getting colder out, right? And certainly colder than 98.6 even now, isn't it? But you're 98.6, so how do I regulate that temperature in my body? Well, it's blood. Blood carries heat, because heat associates with the water molecules. So, and then again, platelets also help you with friends. They help you with blood clotting. All right, so that's our special connective tissue. All right, last two groups, and these will be quick because we had to spend a lot of time on epithelial and connective, because the next few chapters, skin and then muscles, or skin and bone and joints, are all going to be just putting together epithelial and connective tissue and making organs and systems, right? So muscle is going to get its own chapters, and nervous system is going to get their own chapters. So we don't have to really spend a lot of time here introducing. We want to say, yeah, here's other tissues you should know about. Okay, so muscle is going to be unique in movement. The other, do not mistake transport with movement. That's not the same thing. The movement really comes from the muscles of heart. The blood just allows the flow because it's liquid. But the act of moving, comes with the use of ATP and comes about because of muscle. So that's either moving me, like skeletal muscle, moving substances like blood and digestive stuff, and an airflow. That's all going to be muscle that's doing that. And if the muscle fails, then I fail in getting things into the body and out of the body and around the body. All right. Muscle is unique from epithelial and connective because it's excitable. So it responds to electricity. Right? It is very good at responding to electricity, and so will nervous. Nervous tissue will be. So this is an important property. Again, we're trying to say, how are these things alike? How are they different? Furthermore, this is unique to muscle. It contracts. So contraction for us will be the idea of actin and myosin, two proteins, getting together, right? So here's our muscle. So full of, this is skeletal muscle, and cardiac would look similar, because they're skeletal, cardiac, and smooth. And so these cells, because this is one cell, right here, one cell, right? This is a much higher magnification than that model is of bone. Okay, so this is just one cell. And so all this actin and myosin in here is able to bind. It can physically contact each other, and it can start to move the proteins. On a microscopic level, which then enough of them start moving, it happens on a macroscopic, right? A level you can see, which is what we call contraction, right? What I'm doing with my arm. But ultimately, this ability I have right here comes from all of this, right? So we say muscles contract. And to make it easy, we can say it means it shortens. It changes its shape significantly, right? And you can say shortens, because that's what's going to happen. You're going to see the whole muscle. That's why I said it shortens on the long axis. It widens here, but shortens. All right, and that's what we call contraction. We have voluntary and involuntary, and this is really important. Voluntary means that I'm aware, and I am directing, but more important, I'm aware. Because your brain and spinal cord do most of the direction of muscle. Right? Muscle generally waits to be told that it needs to contract, and it is told through electricity, excitability. But the difference between voluntary and involuntary is, am I aware? So I always ask students, because my online students, they have to turn in a group these questions for grades, all right? So they work together as groups and they turn these in. And I saw repeatedly when I asked about chapter 4, not all the time, not everybody did this, but a couple of students on chapter 4 made the comment that smooth muscle was voluntary, and I'm like, how? Have you ever been aware that food was moving from your stomach to your small intestine? Right? Where do you know that? Have you ever been aware of your blood vessels, right, doing constriction or contracting or relaxing, dilation? Have you ever been aware of that? Right? And I mean, I didn't state it sarcastically to them. I just said, no, it's not. Right? It's not voluntary. I'm asking you though, consider what that means. Are you ever aware of your heart contracting? Well, yeah, on some cases you can you can feel or interpret it's doing it, but are you telling it to do that? Are you making that choice? Because I'm making the choice to flex my arm or my fingers or walk or talk, right? I'm not making the choice to breathe right now. It's just happening, thank God, right? Because I'd probably forget, right? And then I'd be in trouble, right? Like Jane is right now. Alright, so you see, I mean, this is what we're talking about, is I need to connect to what my body's doing and what's going on. And that's why I say, look, skeletal is voluntary. If you sever a nerve to a muscle, you have paralysis. Because there is nothing to carry the message from your brain to that part of your body. You have cut the line. Okay? And that can happen because cardiac and smooth do require what we call innervation. They all require innervation. They all require the nervous system to help them out. They work together. But in some circumstances, you are aware of that direction. And in others, you are not. So this is skeletal. This probably looks familiar to you guys right now because you're looking at slides, right? Hopefully it does. Hopefully that didn't surprise anybody. What am I ultimately looking at? Check it out. I love this. This is beautiful tissue, isn't it? You have to look at it under 40x because you can't see these really small, right? They're within the cells. That's a cell, that's a cell, that's a cell, that's a cell, right? These are a bunch of cells. Skeletal muscle is multinucleated, right? It has many nucleus, so it's different in that sense. Many nuclei. But check it, and they line up so nicely, right? So again, this is what's happening. When I do contraction of something, I'm getting a lot of these cells to do the same thing together. And that same thing is shortened. Okay, so what do these patterns that we call striations, stripes, mean? What do they mean? Well, the patterns mean that your actin and myosin are lined up in a specific manner. You are not, this is not as magnified as this. So what do I have here? That dark line? That's where actin and myosin are overlapping. That's where they're in common. And on this one they show myosin is thick and actin as a thinner line. And that's realistic because they are different sized proteins. So when actin and myosin overlap, there's more density. And when it's actin only, the light, there's less density. So we are looking at a pattern of the alignment of these proteins. And we simply call it striation. So when I begin to contract, right, the myosin is going to pull the actin together. And I will use this room as an example to and say, look, your walls are going to close in. And in a contracted muscle, I would lose that light area. This is showing me my potential for contraction. Light, dark, light, dark, light, dark.
So what would that be? What would that muscle be called?
We could call it your gastrocnemius. We could call it your soleus. I mean, at this point, we don't know which skeletal muscle. We'll give you guys about somewhere between 30 and 40 to know in lab.
Okay.
There's about 600 in the body, give or take a few.
So that's not smooth muscle.
So this is skeletal. That's what you're saying. So it's skeletal. This is your voluntary skeletal muscle. This pattern is part of it. It allows it to do its contraction. All right. In smooth muscle, it's called smooth because you don't see the stripes. There's still actin and myosin, but its pattern is different. The way it lines up is different. Cardiac is called striated for the same reason. It still has the actin-myosin overlap and actin only, all the way along. And it will do the same thing that skeletal do. Okay? So, That's really what we're talking about. So there's gonna be a difference in appearance because of some of the function, but all muscle moves. Smooth muscle looks, again, less organized. It's actually only a single nucleus, so that's a difference. They're very spindle-shaped cells, not long cylinders like these guys are, right? And like you saw in the last slide, they're spindles. And so when they contract, they kind of do this kind of close all together, close up and get shorter. So you want to think of the spindle as a big, like I said, big eye-shaped thing.
Where did you say that skeletal muscle is now?
So skeletal muscle is going to be any of this stuff attached to the bones. And skeletal muscle is going to move the bones, which means you move, okay? Because your bones give you support, and as soon as you start to move them, you're going to move, all right? Smooth muscle, this is going to be these linings. They're going to be in the walls of the organs inside your body and the tubes inside your body, like your blood vessels and your respiratory tract, inside the wall of the stomach and the small intestine, okay? It's going to be around glands. And you don't command this muscle to contract. The nervous tissue still does, but you're not aware, and we call it involuntary. And when it contracts, it still does, right? The shortening, it's just its contraction looks a little different than the skeletal. And then cardiac, I said it's kind of in between. It still has light dark. You may not see this so well on this, but it's one nucleus. So it's striated like skeletal. It's one nucleus like smooth. It has these really intense cell junctions. So a junction is where two cells come together. So cells are shorter in cardiac, right? So they're not, like, here could be a skeletal really long, a cardiac could be like this. And then they have another cardiac, another cardiac, another cardiac. And so they have these structures called intercalated discs. And in lab, I tell my students, yeah, that's the way you're going to tell the difference between cardiac and skeletal. You're going to need to find this really dense junction between this cell and this cell, or between this cell and this cell, right? Or this cell and this cell. You don't see all the nuclei on here, so you can't, but that's what that is. Their cells are much shorter. Very much involuntary, not as nicely organized for a reason, right? And just depends on your instructor about. The sole job of this muscle is to move blood. That's what cardiac is doing. It's moving the blood, right? So, like I said, I kind of think of this as a kind of intermediate. And we'll talk more about the idea of cardiac muscle and smooth muscle when we get in future chapters. All right? So, but still needs electricity. It's just, again, your brain is not, you are not aware of its contraction.
Some like lab professors isn't putting that on the practical because it's so hard to fund the disc.
Intercalated disc, yeah. And that's okay. I mean, if your instructor says I'm not putting it on there, then don't worry about it. But yeah, it can be challenging. You have to get, the slide's got to be cut just right. So, all right, last one, nervous tissue, right? So what do I still need to do, right? I got my protection covered. I got my movement covered. I've got my ability to bring things into the body and get things out of cells or the body, secretion, absorption, right? I've got the ability to insulate. I can contain and cushion as connective tissue. So what do I have left? Well, I have a big deal left, don't I? I got my whole responsiveness, that characteristic of life, responsiveness. So the nervous tissue is how we're going to sense, right? Anything at all. So when we start looking at the skin, right? Look a skin model out. This is you guys being in this room, right? Now, first of all, I'm going to give you a little heads up. On your models, nervous tissue is often represented in yellow. Yes, it's just a code for model makers. All right? Now you realize, hopefully, don't fall. All right? That, right? I'm just going to, since there's one right up there, I'm going to put one right up here. All right? You realize that the skin is going to be full, right? Just filled with different sensory. Because this is where you contact the world. This is where you're going to have a problem, right? Perception, that's your higher order thinking, right? The idea that, what does this mean? So I got the idea of I can detect something, which is sensation. And then perception is the idea that what does that sensation mean? Okay? So what's going on with that? And then coordination and control of responses, well, that's making the muscles work, isn't it? Right? Because think about it for 2 seconds. How much different sensory is coming in? The sound of my voices, the sound of other people's voices, right? That's an issue, isn't it? And you have to process that. And you have to decide. Right? The temperature in this room, the hum of those air handlers, right? The smells, the sight, all that sensory is coming in, and your body has to figure this out. Well, that's the nervous tissue's job, isn't it? What does it mean? What do I need to respond to? Right? Now, the cool thing is once we introduce this and say, look, it's always about electricity. It's always about just changing where charged ions are. That's all it is. Is moving them across cell membranes generates action potentials. And that's the way they work. Okay? So, here's what they look like. Now, this caused some confusion. And I can't remember, Amanda, if this is one you had trouble with too, if I made that comment. Okay? Because nervous tissue at first glance may look exactly like this areola. Because nervous tissue is full of lots of neuroglia cells. They're much, much smaller. Right? Okay? They're much smaller. There's a lot more of them. They are the support cells. They're extremely important to nervous tissue. Right? And then neurons, there's fewer of those, but they're going to be much, much bigger. And they look very, very light because they're so large that when they take up stain, it kind of diffuses right through there. So you've got to look for one of those big neurons. And they take on different shapes. All right, so neuroglia are the support cells that nourish, protect, and insulate. All right? And then the neurons themselves, made of cell bodies, right? And then dendrites and axons. Okay, so what do they look like? Well, here's a classic example, right here. Right? So again, cells need to look different ways because of the jobs they do. These are like long, long wires, and that's what you're going to see in an axon, that just reach out down to these muscles. So on that muscle, I'm going to leave you guys with a nice neuron, right? So on these muscle cells over here, I'm just going to show you this connection now because we're going to make it later, but you might as well see it. Right here at the end, that's an axon coming down. Right there, and making contact. And that axon is telling, remember we said this is excitable, but it needs to be told. Is telling this muscle, hey, do something for me. All right? So, sorry, I put that on. All right, so here's what we have, right? Again, cell body, right? Nice central nucleus, dendrites, long axon, an axon terminus. All right? This is just showing you the cartoon. These are support cells around here. They're going to get different functions. We're going to talk about them more in the chapters on nervous tissue. Okay? But that's what you're going to. So when you look at the slides, please look for the presence of that large, diffuse. It'll have a very distinct nucleus, but it'll look really spread out because that's what, right? These neurons look like. They're really, really big. Lots of cytoplasm. Okay? Whoa! Are you okay? I was about ready to lose it there. I think if I had a student, that's going to be the end of my. I'm just going to leave, right? All right. Last thing we have to talk about, and we'll revisit this when we get to skin, and we'll revisit this again when you go on to AP2. All right? Is what happens to repair tissues. Now we do understand that if we damage nerve, which I almost did before Jane, right? And we damage muscle, that we're not going to get the same kind of repair. All right? And that can happen in any injury. Just depends on the extent of the injury. That can happen. But here's we're looking at the skin, right? And we'll realize, okay, here's our, we didn't even bleed in this injury. Look at that, isn't that cool? Right, we just kind of cut down here and they didn't break a blood vessel. But the reality is that really this cartoon should show you a blood vessel breaking, because it really becomes really important when the blood vessels break. Because if I just, and you've probably done this as well, sometimes you have really, really thick skin on your palms and you kind of, something, you felt contact with something and you lost some layers of skin, but there was no bleeding, right? Well, you lost dead skin. So it really, in that circumstance, we're not going to talk about inflammation. It wouldn't happen. But when you affect living cells, this is going to happen, right?
Like spraining your ankle, something?
Well, yeah, but cutting yourself is fine too, right? As soon as I get through these outer dead layers, I'm going to hit a living cell. And if I open up a living cell, right, so this blood vessel is made of living cells down here in the lower layers of the skin, right, after I get past the epidermis, maybe this is showing you the epidermis here, and I'm getting into the dermis here, right, I'm hitting blood vessels, I'm hitting living skin, living cells, I'm opening them up. They're releasing chemicals. That's what the green is trying to show you. These are a bunch of chemicals, because cells are just packages of chemicals, right? And so when any cell is injured, any cell, any injury to any living cell, we're going to start inflammation. So what does inflammation do? Well, inflammation, right, starts because of this release of chemicals from the injured cells, and it basically will do the same things. It'll cause redness, heat, swelling, and pain. Those are your 4 signs of inflammation. And the reason it does is because these chemicals will tell nearby blood vessels that are not broken, not causing you to bleed, right? It'll tell them to dilate, right, get bigger, which means more blood to the area. It'll tell the nearby, and it'll tell these blood vessels, these chemicals will, to increase the spaces between the cells, so more stuff will leave your blood vessels. And what stuff do I want? Well, I want my defenders, right? See all these defenders here in purple? I want them to leave the blood and get into the surrounding tissue. And so they're showing you a cartoon of these things we call neutrophils. But to get them out of the blood vessel, I have to open up the spaces. So I kind of open the door a little bit. So here's my blood vessel normally. Inflammation means I open in a crack, right? And now the cells that are in here, in my blood vessel, can leave, and they can go out and deal with the injury. Right? Now, yeah.
What 4 signals?
So it's redness,
Okay.
heat, swelling, and pain. And redness and heat come because of increased blood flow. So I make the blood vessels wider, more blood comes to the area. Not for bleeding, right? Because you will have clotting on it, but for delivery of more cells. And then the increased spaces is what we call permeability, leads to the swelling. So more fluid, including these cells, leaves the blood and enters the tissue spaces, right? Enters into these spaces and gives what we call edema, swelling. So this is your reaction to the problem of injury, and it will address it. These chemicals released will also get your fibroblasts, right? So your macrophages will eat anything that came in with your splinter or whatever, all right? And then the fibroblasts will help repair. Fibroblasts will make more collagen to fix connective tissue and elastin and such, all right? And then these cells in the epidermis, right, they'll divide more. Because if I heal and you can't even tell I was cut, well, that means that I restored my epidermis and my dermis. Now, if you scar, here's what happens. If you scar, you still did your inflammation, because any injury will lead to inflammation. But the damage you did was so great that the cells in your epidermis could not keep up. They couldn't undergo mitosis fast enough to seal off the skin. And you need to do that as fast as you can. You need the skin sealed off so that stuff stops entering. You want to make sure that stuff just enters through your mouth, nose, places like that. But as long as your skin is broken, right, then microbes can come in all the time. So if you do damage that's so extensive that you cannot get these cells to undergo mitosis fast enough, well, then you get the fibroblasts to just dump a lot of collagen there. And that's why it looks different. Your scar means you just have collagen instead of actual epidermal cells. But the point was, you had to seal off the skin.
So they dump a bunch of collagen.
Yeah, because collagen's just a protein. I can make that really fast. It takes me time to make another cell. And so it's filler, right? You're basically, that's what you're doing. You're filling in the injury with stuff that will work. All right? So that's it. That's again what we're talking about here. And this is easy to relate to because probably everybody in here has scarred themselves, unfortunately. Some more visible than others. I know. Some have scarred themselves, or at least has cut themselves, and understands that inflammation is always the same. You always get a slight tender, red. Again, the pain comes because all the fluids put pressure on the nervous tissue all over the place. Yes.
I have a question. So, I don't understand, like, sometimes if you cut it one way, it leaves a scar, but if you cut the other way, it doesn't. It's in the same, like, area.
It just has to do with the way that the cells get, they replace themselves with collagen. So it may not be visible when it's, because it's in the direction of the fibers, is my guess. That's a guess. And if you cut the other way, maybe you were going against, kind of like against the grain of a cut on a piece of leaf film. But that's a guess, that the fibers, it has to do with the direction of the fibers that they're replacing. Because your dermis is, right, dense, irregular. And so these fibers are running in all different directions. So it may not be visible. If you cut yourself in one way, when they try to replace it, you cut yourself in the direction of the fibers. They're just building those back up there. And you just can't see it. I don't know. It's just a guess. All right. Tissue and aging, yes. Very few things get better with age. All right. We have a variable, what we call senescence is that time period in which we are really not actively changing. We're not really adding a lot of cells, and we're not in active growth. We're just kind of trying to keep up. Senescence is probably that. And it has to do with your genes. You know, what enzymes, what proteins, what things you make, how do you use energy, and your lifestyle influences this, your environment influences this. I said much of what we associate with aging, because it's happening inside our bodies as well, we just can't see them. So we usually say this loss of elastin and collagen are the big deal, right? Because elastin gives us, you can stretch and reshape. Well, if I lose elastin, then I sag and I wrinkle, right? Right? And collagen is supple, flexible, and so it's also. So I said, with the loss of elastin is just a protein, and your fibroblasts, right? I said they're just not keeping up as well anymore. They're not building more stuff. They're just kind of they're just trying to keep up, but they're losing that battle because of time. So you lose tissues through age. Bone does the same thing. You can't build more bone, right? No longer active building. You can't build more bone after a certain age, all right? Nervous tissue and muscle doesn't regenerate anyway, but you just accumulate more damage. That's another way to say this is too, So all through your lives, you're losing some nervous tissue, losing some nervous cells, losing some muscle if you're not challenging it through exercise. All those losses add up, right? That's really the idea of aging. And overall, that's why people who are older don't heal as quickly. We watch these injuries and the rate of repair to try to figure that out. Again, this is a homeostatic imbalance, right? On a big level, aging is. That's what we mean by systemic level. We just can't keep up with the losses. As we started ours talking about the idea of gray hair, right? But there are so many other things to aging that. And, there's always talk about finding things to slow down the aging process, but there isn't anything available at this point. We say, look, do all things in moderation. That's probably good advice to anyone, right? Balance, right? Because we said, ultimately, the idea of maintaining your functioning systems as long as you can is really, really important. We have an aging population. This is a big deal to us, especially as we're embroiled in talks of healthcare systems, because that's a lot, and we just have more and more aging coming into the system, right? So it's not going to get better, right? You don't ever, after a point, if you continue to do damage, which is why I always say to young people, look, go and exercise, go and do some weightlifting, challenge your bones, challenge your muscle. You really, really need this, trust me. Because there'll come a time when you could use those reserves. You could use that ability. Because your body does adapt, but it won't adapt forever. That's the idea of senescence. You're not able to anymore. So I basically, as I talk to aging people, I say, look, you're going to be lucky to maintain. You're not going to recover function. You're lucky to maintain. So keep on moving, keep on trying. Because it's just, you want to prolong your independence. Because a loss of independence is a huge, huge burden on society. Huge. Okay? So do consider that. And you'll be treating a lot of these people if you go into healthcare, right? Because you're not, you can specialize in pediatrics and try to avoid that, but at some point, the majority of your clientele is probably going to be elderly if you're not specializing in pediatrics. All right? So tissue and cancers, right? The number one predictor for cancer is age. Hands down. All right? And again, just like I was talking about, this accumulation of losses of nerve cells and losses of muscle just builds up. Well, your cells have undergone so much mitosis in the epithelium and the connective, right? Because that's where cancers generally start. That it's just probability that you're going to get a mutation in a proto-oncogene or a tumor suppressor gene family. It's just probability. That's all it is, unfortunately. And I say this, I put it under the umbrella of genetic lottery. Right? That's where we all are. It's a great equalizer. But so you can make your risk higher by things that you do, because the things that you do could, right, increase damage and therefore increase mitosis and the need to do mitosis, like smoking, right? Or you could lower that rate by, taking care of yourself and trying to keep your cells from dying any faster than they need to, right? So that's where the environment comes in cancers, right? And so, as we said previously in chapter 3, said, once a mutation in the control of the cell cycle, we said tumor suppressors or proto-oncogenes occur, right? They're not functional. They look different. I said cancer can start with any dividing cell. That's why you're not going to find a cancer of a muscle cell per se or a nervous tissue very often, right? So carcinomas come from epithelial, sarcomas come from connective. Myelomas are not from muscle themselves, but myeloid or blood cells, okay? Because those undergo division all the time. How you treat a cancer depends on the genes expressed by those abnormal cells. You can't use the same therapies just because it's called breast cancer or colon cancer. Really, we have to get a genetic profile of the abnormal cells if we're going to effectively try to treat them. And so if you do know somebody, try to do that has cancer. Hopefully none of you guys know it, but right, you want that. You're going to get the best treatment knowing what went wrong in the cells. All right, try a Kahoot. Alrighty. So, lady. Oops. Do any lights on for anybody, or are you guys good? Keep us in the dark, please. All right. What do I got for you guys? Oh, I believe this is it. You guys want to hear this song? I'm just going to take roll over here, and then I'll start it. Because at least you have to hear the chorus. Okay, it's a cute video, but again, I think this is the ultimate in knowing your material, right? Being able to write a song on it. All right, 9 questions. Yeah. Yep, dense regular. All right, and again, these tendons have these very unique. You didn't have to look at this in lab too, because a lot of times it looks very much like smooth muscle. So your instructor showed you that. All right, but lots and lots of collagen. So this would have a lot of elastin. It would have some collagen, lots of elastin. All right, and found in the tendon, it's going to be this dense regular. All right. So again, just a hey, because you know my test questions are going to ask questions like this. All right. Most of the connective tissues, what's a good generalized? This is what you have. All right, lots of extracellular, right? It is not lots of cells, that would be epithelial, and certainly most of the liquid is really not relevant except for blood, right? It does not do absorption really, and it's not avascular. So type of connective tissue with minerals and provides support. Absolutely. Cartilage does supply support. Say that fast, 3 times fast, right? But it is not made of minerals, right? It's made of what we call proteoglycans, or sometimes they call it a ground substance in general, but it's not minerals. What type of membrane lines the cavities and opens to the outside world? Completely sterile, completely contained, not open to the outside world. So the lion's cavities might have been what threw people for Cirrus, but look, so there's lots of cavities, right? There's cavities within cavities in the body. So really open to the outside world, that's your mucous membranes. And so they're going to have to look different to protect you. What do cardiac and smooth muscle have in common? Cardiac and smooth. Yes, both are involuntary. All right. Which of the following tissues functions to control movement of the body? Movement. Should be totally everybody on this one too. Oh wow. Why?
Because nervous controls movement.
Controls, absolutely. It's the key to the term, isn't it? Don't be throwing my Rita said, what does sex mean? So nervous controls. All right. So don't read so quickly. You're not competing for time. Okay. So, which of the following is a neuroglial cell in the central nervous system? I didn't tell you all these names, unfortunately, so I might throw this question out if you don't. In the central nervous system. Is anybody's guess, isn't it? Well, you should realize that there's only 2 possible answers here. And then you flip a coin. Right? 2 of these things are completely wrong. Completely wrong. Completely wrong. Right? That's a muscle cell. And this is a cartilage cells. Now we have Schwann and astrocytes. And so it was flipping a coin, wasn't it? Don't go to the casinos, anybody. All right, because that was a luck. Again, if it's a question, like I said, I'll throw out questions that I really didn't specifically talk about in PowerPoint, but astrocytes are definitely part of your central nervous system, and these guys, those are the cells that are actually wrapping around this. As you guys will learn, that's a Schwann cell right there. So, and this is not part of your, this is not showing a central nervous system neuron. That's a Schwann cell. So, all right, but I'll throw that out. All right, but I'm going to tell you guys, don't go to the casinos. You're not lucky today. All right. So. All right, which is long is not a characteristic of skeletal muscle. You wouldn't do this, or isn't like this. Oh, look at that again. Gosh darn it. All right, so what were we missing? And again, because I brought muscle in here, and there's things I don't say to you all. So again, I'm not going to hold you accountable. Don't worry, I'm the one who gets to launder your scores, okay? So we do know this, though. This one we should know that cells are cylindrical with lots of contractile proteins. Because I did say that a couple times. And I will say those more times when we get to those chapters, right? So this is absolutely true, and this is not, all right? Cells are controlled by the nervous system. Yes, you should know these two things. That should have been really evident from the presentation, all right? Cells generally have lots of mitochondria. I did not address that, right? They do though, all right? They are, because mitochondria is what provides energy for us. So we're going to see a lot of mitochondria in muscle, all right? You can't see it under the microscope, so it's not really being pointed out to you because of resolution. But this is where my cells make energy, they produce ATP. Cells have a single nucleus. No, I did mention this, but again, I didn't really expect it to stick. It's a minor thing. The muscle cells, skeletal muscle cells, have lots of nuclei, right? Cardiac and smooth only have one. Okay? And gap junctions, I didn't specifically address that. So fair, it's fair that, I shouldn't, but that's why that one was correct. Because again, skeletal muscle, many nuclei, really long cells, lots of nuclei. All right. Inflammation, last one, is a response that causes which of the following to happen? What do I do in inflammation? Oh, man, it's just not fair today, right? All right. So I'll take 3 questions out for you guys. Now, I know I talked about this, but honestly, part of what the Cahoots is what did stick and what didn't stick. So really, the scores are not a big deal. What's a big deal is that, okay, now I know here's an area where I need to study a little more. Here's an area that I just didn't get just by listening to, the story that you told. All right? All right, so vasodilation, I said increased blood flow to the injured area. And increase the permeability, that's what I did by opening the door, right? I said, this lets all these cells that are in here that can protect me out, right? It does not lead to the loss of blood to flush out invader, it doesn't work like that, all right? So, leads to immediate constriction. That happens in clotting. Clotting is a different process than inflammation, okay? You got to keep all your processes straight in the body because they take different chemicals directing different things. So this would happen in injuries, but this is not inflammation. That's not the job of inflammation, right? And I didn't really even talk about apoptosis, but that's directed cell suicide. So, all right. So, that's again, we've got our challenges. I'll probably take out about 3 of those questions, scores for that, just to make your lives a little bit so you're not so uptight about numbers. All right, that leads us to our first system. Yay! First system. All right. Yes, I want that. Thank you. All righty. So, Here, again, and you guys are not, we're a little ahead of the lab right now, just a little ahead, and that's, but you could use a slide of the skin easily on your first practical, just to demonstrate stratified squamous, right? And if you did study dense regular connective tissue, that'd work too, but this is our, again, our first system, first of the 12, that we're, well, technically 11, it's 12, because there's a male and female reproductive, all right? And so we're building, is what I'm saying here. You know, we look in the mirror, we see this all the time, we obsess sometimes over our skin and skincare, and right? And that's fine, but do we really know what it does for us? We know how it appears, we know what we can do to it, we can pierce it, we can tattoo it, right? We can color it. There's all kinds of things we can do to skin. But what is it that skin means for our survival and our homeostasis? All right? So, right? This one should be obvious, right? If I said, okay, take out a piece of paper and tell me anything you know about what skin does for you. I'm guessing you would get that it protects you from abrasions, right? You might not understand that it protects you from sunlight, but you're going to. You probably get that it keeps bacteria, pathogens out, and it keeps water from leaving. You've got a lot of water, a lot of fluid in your body. You'd rather it stayed in there, okay? So it's a very protective system. And this goes with why it's epithelial, because we said, right, it absorbs, secrete, protect. So skin is not going to be, as Jay and I talked earlier, not today, but another time, we said it's not an absorption. Your skin really isn't that stratified, many layers. Means that I'm not going to easily pass stuff that comes out that I'm putting on my skin or that's outside here in. All right? Yeah, things might enter into the outer layers. If you change the chemistry of it, it will absorb better. Some things can absorb better than others. And they may make it down to the blood. If you put enough of that concentration of that chemical on your skin, it may get into your body, right? So, but typically it won't, because again, there won't be a high enough contact and concentration. All right? It's clearly my sensation, as we were talking about with the nervous tissue. This skin here is full, just all over the place. Sensors. Sensors, not for sight or smell or taste, but for temperature and touch, right? Pressure, pain. That's got to be there. So we call those, we're going to call those the general senses. So I got to be able to do those. Something else your skin does that you might not have realized is transforms vitamin D. So you meet your vitamin D daily requirements through functioning skin, right? So it has this compound called dehydrocholesterol. It's a lipid associated with the lipids in your skin, lipids that are wax-like, so they help keep water from being lost. So this compound, when exposed to enough energy, UV light, will actually start the production of vitamin D, or start the conversion, I should say, conversion. Regulates temperature. So this is your interface between the outside world and the inside world, that stuff stuck in all those cavities, right? Protected by all that muscle and bone. So it regulates, makes sure that your internal temperature stays at 98.6, no matter what happens out here. It excretes waste, so you lose some of the chemistry, that byproducts, stuff that, you know, all this biochemistry you're doing all the time, you produce things that you don't need and don't want and would be toxic. So, yes, please.
So the difference between secretion and excretion, whenever a cell creates something, like that's secretion, but excretion is like when it's just getting rid of something that's already there.
Okay, it's technically, it has to do with where it goes. So if you excrete, it exits the body, right? It's out of the body. The secretion's just out of the cell somewhere inside the body still. So when I secrete saliva, it's into the cavity. It doesn't mean that I can't have waste stuff in it and things like that. It just means that it's still in the body. If I excrete it, it is exiting the body. It's out. It's completely free. So that's why urine is excretion and feces are excretion, and sweat, in this case, would be an excretion. Okay? We'll still call sebum a secretion because it still stays in some contact. I mean, it's coating the skin. But the loss of salts and some small metabolic waste by sweat it's not coming back. We're not using it. It's not staying around. So it's usually that. So skin, in a very simple diagram here, now we're putting together these types of tissues we talked about in chapter 4. Again, you've got your epidermis, right? And notice how the epidermis actually is going to invade the center. So from here up is epidermis. From here to here is dermis. Okay? And the same thing is showing up on these models I passed out to you guys. You've got your epidermis, right? It's clearly the outer part, and then a very thick dermis, really thick.
And that's the inner.
Yeah. And so collectively, this is a cutaneous membrane. Right? Different than mucus, different than serous, different than synovial. And the difference comes down to the tissues, right? So I always use like a serous membrane. A serous membrane is simple squamous and loose areolar tissue. Because remember, membranes are generally epithelial connective tissues. And membranes contain things and separate things. In this membrane, cutaneous, right, it's stratified squamous and mostly dense irregular. Dense irregular that we were talking about, Katie. So dense irregular because of collagen fibers, which are a lot of this protein. The collagen is running in different directions. Different planes. All right, and so this whole thing becomes the membrane that we call cutaneous. And that's why when you get a subcutaneous injection, we are injecting down here. This is also called the hypodermis. You can have a hypodermic needle or a subcutaneous injection. And then there's intramuscular, there's intravenous, right? Different routes of delivery. So why is it that you do subcutaneous injections and use a hypodermic needle? What does that do for us? Think about it. Blood. Blood is the way we deliver anything in the body, right? The blood up here is not, it's not even in here, because this is epithelial, and we said epithelial is avascular, no blood, right? We have blood vessels in here, and lots of blood vessels, but here's where they started. Here's the big blood vessels that then became smaller and entered into the dermis. They branched off and got smaller and smaller and smaller until they became capillaries, right about here, and some areas in here. When I give an injection to the subcutaneous layer, I'm delivering this medication very quickly to the blood. That's what I'm doing. And we said, you're going to see this. The hypodermis is basically fat. Now, and fat tissue allows blood vessels through it. Remember in bone, when I wanted to put a blood vessel in, I had to build a tunnel. Well, fat doesn't do that, does it? Because fat's just this loosely organized cells. So they give way, right? They get out of the way so that blood vessel comes in. But not like that chair. The chair would get out of the way for me, right? You see how that works? So you're always going to see lots and lots of blood with adipose, with fat. It's typical. All right? So all this blood coming in. Now, this is really cool when it comes to temperature regulation too, by the way, if you hadn't thought about it. So this is where heat would be. Heat would be in these blood vessels because, right, all this heat generated from all these energy conversions in my body, because anytime energy is transferred, you always get heat, right? Always. That's the second law of thermodynamics. And so this heat being generated all the time because of all these active cells in my body, right? Well, they're dumping this heat. It's moving, radiating, or conducting into my blood. Because my blood is mostly water. And water absorbs heat, doesn't it? Right? That's why it takes so much energy to boil water. It's very, very stable, and it keeps absorbing all this heat. Well, that's what your blood is. So it's pulling away this heat all the time. And it circulates it all around the body, taking it where it's needed. Well, if it's excessive heat, I want it out of the body. So as this blood comes through with all kinds of heat that was generated in here, right? If I make these blood vessels bigger, I get more flow, and that means more heat. And that heat radiates out, right? Because that would make these ones get larger and these ones get larger. The only thing that wouldn't get larger would be the capillaries themselves, because they don't have any muscle in them, right? The muscle is what allows you to dilate, right? So you get all this vasodilation when it's hot inside the body. You look red, and you feel hot, but that's what's happening. You're controlling heat, because the only way you can lose it is through the skin, all right? And so there's a big thing to look at too when it gets cold, because I said the only place to lose it is through the skin. So when it gets cold, what am I going to do with these blood vessels? Constrict them. Yeah, I'm going to make them really as small as they can get, decreasing blood flow through the skin, so my skin becomes cooler and looks a little paler, but I am conserving heat, right? That's how it works. I just have to figure out who's going to control that, or who's going to know that I'm hot and cold, but that's another chapter. What I need to get is that that's a really easy thing to do, which is why I can say that regulates temperature. Yeah. All right. Now, something else that's really cool if you didn't think about this is think about if you own a house, right? Where would be the most effective place to put insulation? Right? I just want you to hold on to that a second, right? Because your heater in your body, your heater's in a centralized location in your house, and you're moving the heat through the house in a duct system. Is that about right? Which kind of should look similar to this, right? Because your duct system is your blood, right? And your heater is pretty much your muscle. Because that's the only source of heat in the body. It does the most energy conversion, so it is the most likely source of heat. Okay? So if I want to keep the heat in, right, I'm going to put some insulation in my walls, aren't I? And generally it's on the inside of the wall, right next to the wall though. And I want to keep the heat in and not have because the place of exchange is my wall, isn't it? My walls, my windows. So if I insulate inside them, I can conserve this heat. Well, think about what you've done. Muscles down here, here's your insulation, right there, cracked. It's a perfect setup. This is the rest of your wall right here. So you get your generators, your heaters inside, and they keep the heat inside. Because believe me, whether or not you trust me on this, whether or not you think about it, right? That you're not going to spend most of your life at 98.6. Not in a world that's 98.6. It's usually going to be lower than that. So you have to figure out a way to keep your heat. Well, this is a great design, if you think about it, right? So this is going to be our protection right here, big deal right here, in this outer epidermis. This is going to give me my secretions, right? With my glands, like my sebaceous glands right here, and my sweat glands that we talked about when I brought these out when we were talking about glands. Right, here's my sensory. I said it's even yellow in the pictures. Isn't that great, right? You know, they make these model makers and these artists, they all keep these same color designs, right? Your arteries are usually red and your veins are usually blue. No, you can't always depend on that, but there's coding here, right? So we want to give all these functions, 5 functions, to somebody in this scheme. So your epidermis is going to be outstanding protection on. That's really what we're going to give it, and we're going to show you why here. Your dermis, it's going to be this full of glands, full of nerves, full of blood vessels. It's going to have some muscle in here. It's going to be really, really a rich tissue. And again, collectively, this part is your skin, the epidermis and the dermis. The hypodermis is really the subcutaneous. The skin is cutaneous. Now, I am perfectly aware that there's a number of you that will be very, very nervous on Thursday, right? Right? Because you have your first practical. Please understand, I will be recording.